And yesterday what we were looking at is basically solving exponential equations. We also looked at continuing to apply exponential growth in terms of money, which means that we were also looking at some examples yesterday dealing with applying this formula that can be found on your formula sheet. So there were two kind of branches to yesterday's lesson. The first one was solving exponential equations. And if you're going to solve an exponential equation like the ones in questions 4 and 5, you have to do so by rewriting the equation so that everything has the same base. And essentially, if you can whittle the equation down or manipulate the equation in some way to get a base equal some expression of x equal to the same base equaling an apparently different expression of x, but the bases are the same, then what you can do is you can put those two exponents together. And this is why I said apparently different expression in terms of x, because really they're equal. They have to be equal if the bases are equal. So for example, if we take a look at 5a, where we have 4 raised to the 3x is equal to 8 raised to the x minus 3, both 4 and 8 can be expressed in base 2. So 4 is 2 squared, 8 is 2 cubed, and what that means is that we can write the 4 as 2 squared, and we're raising it to the 3x. We can write the 8 as 2 cubed, and we're raising it to the to the x minus 3. The placement of those brackets is important. It's a detail that needs to be written down when you're showing your work. I do understand that many of you are capable of seeing that 4 to the 3x is 2 to the 6x without physically writing this line down, but I think it needs to be written down in a written response, and I would caution you about not writing that line down, even if it's multiple choice, because you could very easily make a mistake. Good morning, everyone. Over here, you're going to have 2 raised to the 3x minus 9. And the property of exponents that I've used in going from here to here is basically that if you have a to the b quantity raised to the c, it's equal to a to the bc. So now we're at that stage, if you look at the bottom line that I've written here, 2 to the 6x equals 2 to the 3x minus 9, we're at the stage where we can drop the bases because the bases are the same. And it becomes then a very simple equation to solve. You're now left with solving 6x equals 3x minus 9. And you can subtract 3x from both sides and divide both sides by 3. I think you're going to end up with x is equal to 3. Thank you. You're going to get negative 3. Thank you, Ryan. Because when you subtract this 3x, you'll get 3x equals negative 9. Just before I take any questions that you might have, I know that there are some errors in the key for question 11 and 13. I suspect that if you were to look in the back of the textbook, if you're using a physical textbook, you will have already seen that somebody has crossed out those answers and written the correct ones. If you are working on a digital copy, it didn't occur to me to do this. I should change the digital copy answers. They've got some. Somebody was just not thinking clearly when they wrote these out. Anyway, does anybody have any questions you would like me to go over from this entire assignment? Zebby? 7F. So in the case of exponential equations where a common base is not possible, then what we have to do is either solve it graphically or using a kind of guess and check, which is called systematic trial and error at this level. And that's where we could use our tables. So 7f gives you 5 raised to the t minus 2 equals 4 raised to the t. You're directed here, everybody, to solve this equation graphically, but quite frankly, until we learn how to solve it algebraically, I don't care how you solve it. If you want to solve it by poking around in your tables for y1 and y2, you can do that. I think solving this graphically could be a little troublesome, but let's take a look at what the graphs look like. Of course, t is our x, right? So I'm going to enter 5 raised to, and I do need to put that exponent of x minus 2 in its own set of brackets. Otherwise, what my calculator will think I want is 5 to the x and then subtract 2 from 5 to the x. But I want to subtract 2 from x before I raise it as a power of 5. And then I'm going to have 4 raised to the x for the second one. Now, I do know something about these graphs. 4 to the x, if I were to look at 4 to the x, that's one of those very basic exponential functions that we've talked about, c to the x in your textbook, or b to the x, or a base to the x, where the base is greater than 1. And it will have a y-intercept of 1, and it will increase because the base is 4, greater than 1. The 5 to the x minus 2 would also go through here, but it would be steeper before I shift it. So let me rephrase that. 5 to the x would go through that y-coordinate of 1 on the y-axis, but then I shift it to the right 2. Now, I don't know what that's going to look like, if it's going to be here or here. I really can't tell by looking at my work here. I can't tell by looking in my brain, is what I'm trying to say. So I'm going to need the help of the calculator. Because if 2 corresponds to that shift, we can see where they will intersect. If 2 corresponds to that shift, we kind of figure out that they're going to intersect up there. But they will intersect. I'm going to go zoom 6 to begin with. So I know that since the one with the base 5, I could be wrong here, but I know that it increases more rapidly, so I believe they're going to intersect way up there someplace. Then again, this is the downside, everybody, of doing something graphically. It's not entirely obvious. If I were to trace these 2 graphs back to the left, will they intersect? I don't believe they will, but I'm not willing to commit myself to that. My thinking, and it could be flawed, is they won't, because the one with the base 5 gets closer to the x-axis, moving to the left more rapidly than the one of base 4 does. So I believe that the 5 to the t minus 2 will always be below that. What would happen if we were to just try intersect right here without actually knowing where they intersect or seeing the intersection point? And I'm asking that question genuinely because I don't know. I think it can calculate it. I think. No. So I'm guessing that what we're going to have to do is look up quite high. I was always assuming that if you could see the domain where they're going to intersect, that the calculator could do it. But let's go up to, I don't know, 100. We could certainly cheat by looking at the answer and then trying to reverse engineer it. But and the problem here is going to be that I won't necessarily see it. I'm zooming out so much. You know, maybe they do intersect to the left. It seems to me that the one with the base 5 should be steeper, so it should eventually intersect. I want to resist the urge here. I want to solve this algebraically. And you will learn how to solve it algebraically in the coming days. But I'm going to go over to negative 100 as well. I don't think I changed that. So here's where I'm suspecting, am I right, that they're intersecting way, way up there. So we're going to have to really increase the y. My original thought was correct, that since the base 5 is more than a base 4, it's steeper. You know, I might really want to use a combination here of looking at my tables and looking at a graph in order to find it. So I'm going to start at 0 and I'm going to go up by, well, let's just start by going up by 25. We can pick any number we want, but I think we're going to have to, well, maybe we don't have to go up that high. Let's go up by 1. Let's just see what happens first. This is a weird question. I want to go back here. So y2 is more. It's still more. y2 is more, more, more. Looks like y2 is always more. Keep going. This is really trying my patience. Oh, look at that. Someplace between... By the way, those e's mean multiplied by 10 raised to a power of whatever that next number is. So y1 at 13 is about 48.8 million and y2 is 67 million. At 14, y1 is 244 million and y2 is 268. And then all of a sudden, between 14 and 15, it changes. So... man, what a drag, because now what you have to do is say, we know it's someplace between 14 and 15, but if we want to solve it graphically, apparently with this calculator, you need to put your y max in your window settings up high enough to see. I don't think we're going to see it with our eyes, but for the calculator to see it. So I'm going to go up to 1.5 multiplied by 10 to the 9. And hope my calculator doesn't explode. Well, I'm going to go up to 2 multiplied by 10 to the 9. I don't think we need to go from negative 100 to 10. We've already established that the intersection point is between 14 and 15. Was that my memory right there? So, I mean, we could just go 14 to 15. I'll go 0 to 20. I don't really think that matters as long as that domain of 14 to 15 exists on the screen. I don't know what you're not even going to see these. Well, you might see them overlapping. I was going to say you're not going to see them overlapping. Well, yeah, you do. So perseverance, what Mr. Smith, my social studies teacher, would have called stick-to-itiveness in junior high, is what's required here. You got to just keep going. No, we should be getting something between 14 and 15, and we do. It's a very challenging question, and if you saw this question on an exam, or if you saw this question midweek next week where we know how to solve this algebraically, I'm not saying that to solve this algebraically will be easy, but I think it's going to be easier than this. At least you're going to have a set of rules you can follow on paper to algebraically rearrange for t, as opposed to kind of poking around in the dark. And, you know, if you did this on an exam, little lesson to be learned here, if you're doing this on an exam, you know what happens, right? You start to sweat, either physically or mentally or both. And then your brain starts to not work very well. And that causes you to panic more. I think we've all experienced that, right? And never leads to anything good. Other questions? Go ahead, Ryan. 13? So, were you here in class yesterday? Okay. Did you watch the video? Okay. So what we're dealing with here is compound interest. It's compound interest because it's an investment, and then it says you get a certain amount of interest in a % per year, but it's compounded, and it's compounded semi-annually. What semi-annually means? What semi-annually means? Okay, I'm just going to go a little bit further though. Semi-annually means twice a year. And what that means is that if this represents left to right a year, so the left-hand side is January 1st, the right-hand side is January 31st, what you get is 6.6% in the whole year, which means you get 3.3% here and 3.3% here. And that means that when you start compiling a list of the values of the parameters, P is 103.3%, which is 1.033. So let's just be clear here. I think everybody should know how to do this, but I don't want to leave anybody in the dust here. What we're doing is we're saying that 6.6% gets divided by 2 because we get it doled out or portioned out in 2 pieces, which is a good thing. It's better than getting it all at once at the end of the year. And then we say it's 100% plus the 3.3. And if I divide that by 100 because it's percent, this is our, what we would call in Math 20 our common ratio for a geometric progression or sequence or series. A is the original amount, which I believe was 500 clams. And I wrote this in the wrong place. B, the base, is 1.033. I'm not sure what I said, whether I said B or P, but if I did say P, I was wrong. I misspoke. B is 1.033. P is the period of time it takes for you to qualify for that 3.3%. And since it's twice a year, P, if I want to work in years, is 0.5 years. And when you put those 3 things into y equals a b to the t over p, that becomes the amount of money. I'm just going to use a for the amount of money. We could stick with y is equal to 500 multiplied by 1.033 raised to the t over 0.5. And I don't know what the textbook says, but you could write a equals 500 times 1.033 raised to the 2t. Because when you, 0.5 is a half, right? So no matter how you look at it, t over a half is 2t. You could multiply top and bottom by 2. You could flip the fraction over. Anyway, that's the equation that you're going to be working with to answer B and C. When you answer C, you're simply going to substitute in 1500 for A because it asks about how long it takes for it to triple. And then you're going to solve it graphically because, again, you know, it'll be a few days before we learn how to solve these exponential equations that have no common base, how to solve them algebraically. Are you fine with that, Ryan? Okay. If you don't mind me asking, what was it that you had done?
For P, I put 0.2 for some weeks.
I understand that. You put 2.2. You had the number 2 in your head because it's compounded twice a year.
I don't know, I was thinking.
No, and that's fine. There's a lot of weird ways to approach these, and I can see why you would say 0.2. By the way, you should be familiar with the idea that, quarterly is 4 times a year, semi-annually is twice a year. We could have monthly, which is 12 times a year, and you're going to be getting an assignment here in this unit right away. I'll probably give it to you tomorrow, but you won't really know how to solve it algebraically, which is what I'm going to want until Tuesday of next week, maybe, or maybe even Wednesday of next week. Any other questions? Go ahead, Farhan. Right, and that goes to what I said here about the answers in the back being wrong. So if you're working in with a digital version of the textbook, you will have the wrong answers. I think, is it the case that when you look in the back of your physical textbook, somebody's crossed it out probably and written that? Okay. If some of you, yes. Some of you have maybe a textbook that's never been used before. Anyway, this is wrong, and this is correct.